Hello lovers, in this video we're going to go through our Edexcel Separate Science Higher Tier Physics Paper 2 that we've written for 2024. So after each question comes up, pause, have a go at it yourself and then play the video and we can go through the answers together.
An investigation was carried out to find how the number of turns on a coil affects the strength of an electromagnet. A wire was wrapped around a large iron nail, and the wire was connected to a battery, as you can see in this diagram. This formed an electromagnet. The number of paper clips that the electromagnet would pick up was recorded, and the number of turns around the iron nail was increased, and the method repeated. A simplified diagram of the electromagnet is shown below. Here we're asked to draw the magnetic field pattern around the electromagnet. So here is the diagram that you need to draw. Now the key features that we need to include in this question. One of them is that the magnetic field lines have to point from north to south, and that's always the case. We should also know that the magnetic field lines are never going to cross each other. That will never happen. And it's also worthwhile knowing that the closer together the lines, the stronger the magnetic field. So as it's like leaving the ends of this electromagnet, you can see that the lines are closer together, and that's where the magnetic field will be stronger. So this is the general shape that you need to know. The magnetic field pattern around an electromagnet is exactly the same around a bar magnet. So if you learn it once, you know it both times. Now we're asked to explain why the field inside the electromagnet is strong. So the reason for this is that every little coil of this electromagnet is going to have its own magnetic field. And what's going to happen is the magnetic fields from all of the different coils are going to add together to provide you with a stronger magnetic field. And so that is your answer. The field inside the electromagnet is strong because the magnetic fields from each coil add together. The results were plotted on a graph. Here we're asked to start off by drawing a line of best fit. So here is my line of best fit. We need to make sure that whenever we draw a line of best fit, we use a ruler and a pencil. And it is a general guide to make sure that you've got around as many points above as below your line of best fit. However, there's always going to be a little bit of leeway with it, which is why any answers that are dependent on your line of best fit will allow a bit of leeway because you'll never ever get it perfect. You're not a computer. So now we're asked to predict how many turns on the coil would be required to pick up 5 paper clips. So if I now return to the graph and my line of best fit, I can see that 5 paper clips, if I read along and then down, corresponds to 130 turns on the coil. Notice we couldn't have done that if it wasn't for our line of best fit. Now, an important thing to remember here though, is you might have got a slightly different answer to me there. It's really just going to depend on your line of best fit. It might be a little bit steeper, a little bit less steep. The mark scheme here will allow any answer in the range of 120 to 130. So there's a good range there. You don't have to get it perfect at all, okay? So that there would be my answer. Don't panic about getting the exact answer on the mark scheme because of course your line of best fit will be slightly different to the one written on the mark scheme. Now we're asked to explain the relationship observed between the number of turns on the coil and the number of paper clips it can pick up. So this here is an explain question. Obviously we can see the relationship is that the more turns on the coil, the more paper clips can be picked up by this electromagnet. However here, because this is an explain, we need to talk about the science behind it. Why is it that it increases? So for this 2-mark question, we need 2 key points. The first thing that we want to state is that more turns on this coil will induce a stronger magnetic field. That's the first point that we need to get across. Our second point is clearly making it clear that a stronger magnetic field means that we have a stronger force of attraction, and therefore we can pick up more paper clips. Now they would be the 2 points that we need to state to get our 2 marks in this question. Now we need to suggest a limitation of this experiment and give an improvement. Suggest questions can be tricky because there's no obvious answer, there's nothing that you've learnt specifically for this. Instead, we need to use some general knowledge and some deduction. So in this question, we're limited by the size of the paper clips. We've only got 1 paperclip, 2 paperclip, 3 paperclip. What about if it could actually pick up half a paperclip or a third of a paperclip? We're missing out on that important information. So a way that we could rectify this and improve it is by simply using smaller paperclips. So now we need to suggest how the reliability of the experiment could be removed. And whenever we talk about improving reliability, let's always say, let's do some repeats. Finally here, we're told that electromagnets are used for door locks. And for a simple 1 mark here, we're asked to explain why. So the key feature of the use of electromagnets in door locks is the fact that they can be switched on and off. Because of course we need to be able to open the door again, don't we? We don't want it to be locked forever. Electromagnets, by turning the current on and off, enable you to turn the electromagnet on and off. So that's our answer to this one. That's all we need to say. Light-emitting diodes have many uses. They're used in many electrical devices, including remote controls and traffic lights. Here we're asked to describe what a diode actually is. And this is a little definition that we need to know. So if you don't know it, get yourself out a flashcard now and copy it down with me. So a diode is a component which only allows current to flow in one direction. And that's all we need to write down there to get our mark. In this question, we're talking about light-emitting diodes. So if we were asked about a light-emitting diode, then we would still give the same definition, only we would add that light is emitted in this process too. Next up, we're asked to describe the energy transfer that occurs in an LED, a light-emitting diode, when it's connected to a circuit with a power supply. So here we need to know what it begins with, and of course initially it's connected to a power supply, so it has electrical energy to begin with, and then it transfers it to light energy, and that's why it can emit light. So we can say that in a sentence, or we could write it like I have here, but you would get your 1 mark either way. Now we're asked to sketch the IV graph for a light-emitting diode. So there's a few of these that we need to know off by heart, perfect for flashcards. For a light-emitting diode, or any diode for that fact, the current stays very close to 0 for negative potential differences, and only when it becomes a positive potential difference does it begin to increase. And then it increases with an increasing gradient. And don't forget, the reason why it stays so close to 0, that current, for negative potential differences, is because of that definition of a diode, the fact it only allows the current to flow in one direction. And we're seeing it here in this graph. So here we have a big 6-mark question. We're asked to describe an experiment that will find the IV graph of a light-emitting diode. And we can use a circuit diagram in our answer, and I think they're a really useful way to aid our explanation. So let's start off by drawing our circuit diagram. Now the first thing I'm drawing is the symbol for a light-emitting diode. So what we have here is this triangle with a line against it with 2 arrows pointing away. That's because it's a light-emitting diode. A diode alone wouldn't have those arrows. Then we have that diode connected in series with a power supply and also an ammeter. Then we're going to place a voltmeter in parallel. Now, the reason why we have that ammeter is to measure the current in this experiment. And we always want to have ammeters in series with the component that we're measuring. So then we also have a voltmeter, which is the circle with the V in it. Now, voltmeters always need to go in parallel with the component that we're investigating. And the whole point of a voltmeter is to measure the potential difference or the voltage in the circuit. So there's one last thing that we need to add to this circuit diagram that we're missing at the moment. So we need to have a way to vary the potential difference. And the way that we're going to do that is by adding a variable resistor. A variable resistor looks like a rectangle with a diagonal arrow going through it. So now we've got this circuit diagram set up, and by drawing it and labelling it well, already actually we've got quite a good chunk of these marks in this question. So now let's describe what we're going to do. So once we've set up the apparatus in this way, we're going to record the potential difference and the current. Once we've done that, we're now going to use our variable resistor to change the potential difference. Once we've done that, we're now again going to record the new potential difference in current. Again, we're going to use our voltmeter to measure potential difference, and we're going to use the ammeter to measure the current. Now we're going to use that keyword that we use in so many of these investigation questions. We're going to repeat this process, because the more we repeat it for slightly different potential differences, the more data points we'll have for our graph. Now, once we've done this, we'll notice that we're only getting positive potential differences. So we're only really getting half the graph. What we need to do now is reverse the power supply. By reversing the power supply, we're now going to get negative potential differences. And now we're going to repeat the process before of recording the potential difference and the current, and then using the variable resistor to change the potential difference and repeat. So once we've done this now, we're going to have many data points for both positive potential difference and negative potential difference. So now all we need to do is plot a graph of current against potential difference. And this, of course, was the aim of the game. When we go back to the question to reread it to check that we've got everything down, you can see that we were asked to describe an experiment that would find the IV graph of a light emitting diode. We've done that here. So you see there's a lot of points we can say here. In these 6-mark questions, we don't want to limit ourselves just to saying 6 points. In any other question, that's a fine method, but these 6-mark questions, instead we're being marked slightly differently. We need to make sure that we give as full an answer as possible and not just giving a few points that we'll do at the beginning of the experiment. We make sure that we talk our whole way through from the beginning, the middle and the end of this experiment, and we talk about any apparatus and measurements that we need to take. So there we are. This would be our perfect model answer. This is a very common question, so by all means, get writing this down and get learning this. The electricity produced in power stations in the UK has an alternating current. It's transported from power supplies to homes where it's used in the mains electrical supply via the national grid. However, batteries used in the home provide a direct current. Here we're asked to describe the difference between a direct current and an alternating current. Now this is a pair of really important definitions, so if you don't know them already, then now's the time to make a note of them. A direct current is a current which will only flow in one direction. And like the question told us, batteries are an example of a power supply that uses a direct current. Now, alternating currents, on the other hand, are currents which regularly change direction. And again, like the question tells us, the national grid and the mains electricity power supply is an example of a power supply that has an alternating current. So those two definitions are very important. In this question, you'll get 1 mark for each of them. If you don't know them, then now's the time to pause the video and write them down. So, next up, in the UK, the mains electrical supply has specific frequency and potential differences. Here we're asked to complete the table. Now this is purely a recall question, okay? We need to know that the frequency of the mains electrical supply in the UK is 50 Hz and the mains electricity's potential difference in the UK is 230 volts. Now, just like the definitions of direct current and alternating current, these are just simple facts that we need to know, and the only way we're going to learn them is by making a note of them and making an effort to get them in our heads. So if you don't know them, now's the time to write them down. Plugs connect devices in the home to the mains electrical supply. So here we have a nice diagram of a plug. We're told that plugs are designed to ensure electricity can be used as safely as possible. And here we're asked to name 2 of the features of a plug that is designed to increase their safety. Now there's a lot of things we can say here. We can mention the fact that we have an earth wire. We could mention the fact that we have a fuse, which is just here. we can mention the fact that we have this outer plastic insulation so that when we touch the plug, we're not touching any of those cables. We can also mention the fact that the wires themselves are colour-coded so that we can look at them and tell which one is the live wire, tell which one is the earth wire. The final thing we could mention is the fact that we have a cable grip, which is this bit just here, which is going to prevent the wires within the plug from becoming loose. And those are a good 5 different options that we could say that would make sure that we get our marks. Exposed wires are an immediate safety hazard. In the event of an exposed wire, the appliance should not be connected to the main supply until it's repaired. Here we're asked to explain why an exposed wire could cause a person to get an electric shock. So this is a 4-mark question, so they're asking us to be quite specific in the points here. Now I'm going to write down a few options that you can say, 5 different marking points, and any 4 of these would get us our marks. So the first thing that we can say is quite simply, if it becomes damaged in this way, then the live wire may become exposed. And it's the live wire that is the dangerous wire. So if we say something now specific about that live wire, the potential of the live wire is 230 volts. Now the person who might touch this wire and become exposed to this live wire is only going to have a potential of 0 volts. And this is where the danger comes in, because what we have now is a large potential difference between the live wire and the person. Now, when we have this large potential difference between the live wire and the person, what we can see is a current or a charge pass from the live wire through the person's body. And of course, this is what can lead to that electric shock that the question is telling us about. So you can see this is a 4-mark question explaining why an exposed wire could lead to someone getting an electric shock. And here you can see I've written down 5 different points that would each get us one of those marks. So if you missed one of them, that's fine, you're still going to get full marks. But I think this is a really good explanation to learn in case you were to get a 4-mark question asking us about the dangers of exposed wires. The national grid transfers electrical energy from power stations to homes and factories. Transformers are used in the national grid, and the national grid is shown in the diagram below. The different parts of it are labelled A to E. Here we're asked to write the correct letter in the box to identify a step-up transformer. In this case, B is the step-up transformer. We should know that the step-up transformer is always placed between the factories and the national grid, because what it's going to do is step up that voltage to much higher levels for transport along the national grid. Next up, we want to identify the step-down transformer. Now in this case, that is transformer D. We always find step-down transformers after the national grid and before homes. And the whole point of them is to step down the voltage so that it's at safer levels ready to go into our homes. Explain the importance of step-up and step-down transformers in the national grid. So this question, very common, really straightforward in what you need to say. So if you don't know these answers, then when I've finished, pause the video and make a flashcard on it. Okay, so first up, let's start with a step-up transformer. So there's only 3 things out of what I'm going to say you could say to get marks in this question. The first thing we want to state is that a step-up transformer increases the potential difference. Then we also want to state that the knock-on effect of this is it decreases the current. Now we want to understand why this happens. So the whole point is that it's going to reduce thermal energy transfer to the surroundings. Now the whole point of this is to increase efficiency and to make sure as much electricity as possible gets from those factories to the homes. So there we have 4 potential things we could say about step-up transformers. Because this is a 5-mark question, we want 3 to come from step-up transformers and the final 2 to now come from step-down transformers. So we should know that the whole point of a step-down transformer is to decrease the potential difference and therefore to increase safety. We do not want to see the high voltages that we see in our national grid in our homes. We want it to be 230 volts. Okay, so summarising, a step-up transformer increases potential difference, so up means increases the potential difference, whereas a step-down transformer decreases potential difference. And the whole point of a step-up transformer is to decrease the current, reduce heat loss, and increase efficiency, whereas a step-down transformer is all about making things safer for our homes. Transformers are also used in many other applications, including audio systems. A transformer was used to decrease the potential difference from a 230 power supply to a 24 volt required by a low voltage speaker. The current in the speaker is 8 amps. Assume that the transformer has 100% efficiency. Explain why it's unlikely that in reality it does have 100% efficiency. So the reason for this is that in reality, energy is usually dissipated to the surroundings. We could say that the energy gets wasted. Now, the most common way that this is transferred to the surroundings is via thermal energy. So that's why it doesn't have 100% efficiency. Now we're asked to calculate the current of the power supply. And we're given this equation. It's going to be potential difference across the primary coil times by the current in the primary coil equals potential difference across the secondary coil times the current in the secondary coil. And I've written this here in the IV notation just because it's easier to write, and it would be much easier for you in your exams to use that notation as well. Now let's not forget that the primary coil is the first coil, the one attached to the power supply, and the secondary coil is that second coil attached to the speaker. If we think of what information we've been given already, we know that the input voltage is 230 volts, so that would be Vp. We know that the secondary coil has 24 volts, so that would be Vs. We know that the secondary current is 8 amps, so that would be Is, and we need to find Ip. So if we rearrange this equation to get Ip as the subject. Here, first off, by substituting in the values we know, we have Ip times 230 equals 8 times 24. Ip is therefore going to be equal to 8 times 24 divided by 230. Now that gives me an answer equal to 0.835 amps, and that is going to be the answer to this. Current of the power supply is 0.835 amps. So here we're asked to calculate the energy transferred to the loudspeaker if it's switched on for 2.5 minutes, and we're asked to include a correct unit. So because in this question we're asked for energy transferred, let's remind ourselves of the equation for this. Energy transferred is equal to current times by the potential difference and then times by time. So I'm just writing it in the symbol notation just because it takes up a bit less space. So the reason why we're picking this is because we know currents, we know voltages, and we know time. So this is the logical equation for us to use here. Now we're asked to calculate energy transferred to the loudspeaker. Either we can use the current in that loudspeaker of being 8 amps and the voltage being 24 volts, or because we do have that 100% efficiency, we also could use the current that we just calculated, the 0.835, or we could use the voltage of 230 volts from the primary coil. We can only do that though because of this 100% efficiency that we're assuming. So the time taken is 2.5 minutes. Now we should know that in physics, our time always needs to be in seconds. So we can convert minutes to seconds by multiplying the 2.5 by 60. That gives me a time equal to 150 seconds. So doing my calculation now, I can say that my energy transferred is going to be equal to, let's say, 8 times 24 times by 150. Or you could do 0.835 times 230 times 150. So popping this into the calculator, I end up finding that we have an energy equal to 28,800 joules. And of course they asked us to include a correct unit. That would indeed be the joules. If you were feeling fancy, you might have ended up giving your answer as 28.8 kilojoules. However, I probably wouldn't do that unless I was asked to in an exam, because you're opening yourself up to making mistakes, converting it incorrectly. So I would just get my calculator value and then recognise that energy is measured in joules. So that's our answer. The graph below shows the heating curve for water. It shows how the temperature of water changes as the energy absorbed increases. We're asked in this question to write down the value of A, which is the temperature. So to answer this, let's just evaluate this diagram, okay? So you can see that X is found at negative temperatures. And because it's negative temperatures, it means it's very cold. Now that to me tells me that X is actually ice or solid water. Y therefore is going to be liquid water, and Z is going to be gaseous water or steam. So by recognising those different states, we can see that it's when Y changes to a gas, that's the temperature that we're looking for. And we should be familiar with the fact that water boils and changes to gas at 100 degrees C. Here we're asked to explain what the horizontal regions on the graph show us. So I've included this diagram here for us to look at. So here are the horizontal regions we're being asked about. Now notice that those horizontal regions, the temperature is constant. The temperature isn't increasing at all at those points. The reason why the temperature is constant here is because these are the points where we get changes in state. Now this means that we're going to have the energy being used to overcome the intermolecular forces of attraction between the particles. Now this means that the energy isn't being used to increase the temperature of this substance. The energy is just going towards overcoming those forces of attraction. Now this question here is a 2-mark question. So to be able to get those 2 marks, we need to state 2 key points. I think the most important of all these options is the fact that there are changes in state. We should just understand that of the horizontal regions. But then any explanation as to why the temperature doesn't increase would be your second point. So either we could say energy is being used to overcome the forces of attraction between those particles, or we could say that their energy is not being used to increase the temperature. Either of those can get you your second mark. So now we're told that the water is in different states at points X, Y and Z on the graph. In each of these states, the water has a different density. Here we're asked to explain the differences in the density between the states found at points X and Z. Well, from earlier, we evaluated that X must be a solid because it's very cold temperatures, whereas Z is the gas. Now, any changes in their density are going to be due to these different states. So we can state that Z, the gas, is less dense than X, the solid. That's our first statement that we can make. And now we can get on to explaining why that is the case. So because Z is a gas, the particles are much more spread out than they will be in X, the solid. And therefore, what would be essentially the same mass of this substance is going to occupy a much bigger volume. And that's what's going to have that knock-on effect on the density. So this question is a 3-mark question, so we need to have those 3 points to get our 3 marks. The first thing we want to state is, of course, that Z is less dense than X. Just lay that out to begin with. Then we need to express that in the gas, the particles are more spread out. And then finally we conclude linking it back to density, which is of course mass over volume, and make it clear that although we have the same mass, in the gas it occupies a much bigger volume, which is why it has a smaller density compared to the solid. The density of solid water ice is 916.7 kilograms per metre cubed. Calculate the volume of a 2 kilogram block of ice. So this is a calculation question. We need to write down the equation that's relevant. Here we're being asked about density and volume. So that means we're going to use the equation that density is equal to mass over volume. I always like to lay out the information they give me in the question too. So I've written down what the density is and what the mass is so that it's nice and neat and tidy. So now we know density is mass over volume. Now we need to find the volume. Now to do this, we need to rearrange the equation. Now you may be super comfortable with that, but if you're not, remember you can use the triangle. In this case, the triangle has mass on the top and density times volume on the bottom. The way they work is we cover up what we're looking to find, in this case the volume, and look at the triangle to see what the formula will be. So because it's m over d, the volume is equal to mass over density. So that's equal to 2 over 916.7. So there we are now, we've got our calculation. We just need to put that into the calculator, and that gives me 2.18 times 10 to the minus 3. Or you could give it a 0.00218. There you are, that is question D. The specific heat capacity of water in state X, Y and Z is given in the table below. Here we've got a nice table summarising everything, and we're told that the specific latent heat of fusion is 334,000 joules per kilogram, and the specific heat of vaporisation is 2,260,000 joules per kilogram. Now this question simply asks us to describe the difference between specific latent heat and specific heat capacity. So to be able to do this, really we just need to state the definitions of each of them. So let's see if you remember those definitions. If you don't, then pause the video after I've written them down and make a note of them yourself so that you're not wasting any time and you've got them down and you can get learning them. Alright, so let us get started with writing down the definition for the specific latent heat. So specific latent heat is the energy required to change the state of 1 kilogram of a substance. And that is the definition you need to know. You might hear specific latent heat of fusion or vaporization, but that is just looking at specific state changes going from solid to liquid or liquid to gas. So now let's look at specific heat capacity. Specific heat capacity is defined as the energy required to increase the temperature of 1 kilogram of a substance by 1 degree C, or you could say by 1 degree Kelvin. That is the definition that we need to know for specific heat capacity. It's a little bit longer than specific latent heat because we're talking about a specific temperature increase rather than just a change in state. But I think it's quite memorable, it's quite logical. Both definitions are referring to 1 kilogram of a substance. It's just that specific latent heat is looking at the energy required to change the state, whereas specific heat capacity is looking at the energy required to increase the temperature by 1 degree C. A beaker was filled with 200 grams of 25 degrees C liquid water and placed over a Bunsen burner. Here we're asked to calculate the total energy required to boil all of the water in the beaker. Now this is a clever question, okay? Total energy required. We need to consider here that we need to increase the temperature of that 25 degrees C liquid up to 100 degrees. Then we're being asked about boiling it all as well. So as well as increasing the temperature from 25 degrees C to 100, we also need to work out how much energy we need to boil 200 grams of water. So to change the state from liquid to gas. So it's a sneaky question, and I think it'd be very, very easy for students to miss that final step. So let's have a think about this then, okay? Let's first start with working out the energy needed to increase the temperature from 25 to 100 degrees C. So the equation for this is that the heat energy equals mass times specific heat capacity times by the change in temperature. And that's the equation that I've written down here. So to get that energy, we need to have the mass. Now we have 200 grams of water, but we need to convert that to kilograms. So dividing by 1,000, we get 0.2 kilograms. We then need to have a think about which specific heat capacity to choose. Now because we're talking about liquid water, and we know that Y is referring to the liquid state from earlier, we can say that the specific heat capacity for this question that we need to use is 4,186. So now we need that change in temperature. Now, we know we need to go up to 100 degrees C to boil it, and it's currently 25, so that means that the change in temperature is 75. So that means that the energy transferred is going to be 62,790 joules. So we've done the first part of the question now, and we have some marks for doing that. Now we need to work out how much energy it will take to change the state of 200 grams of liquid to gas. So in this case, the energy is equal to mass times by specific latent heat. And earlier we were given two different specific latent heats. We were told the specific latent heat of fusion or of vaporization. Now, because here we're talking about boiling the water, that means that we need to use the specific latent heat of vaporization, because that is looking at the state change between liquid and gas. So the value of that we were told on the previous page is 2,260,000. So that's the value we're going to use in place of specific latent heat here. So the energy is going to equal 0.2, because we have 0.2 kilograms of water, times by 2,260,000. Now that leaves us with an answer of 452,000 joules. So here we have our two different sections of energy that we need. We know the energy needed to raise the temperature 100, and then we know the energy to change the state of it all to gas. So what we need to do finally to get our final answer is we need to add these two together. So adding these two together gives me 514,790 joules. So that there is our final answer. That's a really clever question. So if you get something like this in the exam, now you know exactly how to handle it. A person is using a wheelbarrow as a lever to transport a load of mass at 20 kilograms. The weight of the wheelbarrow is 90 newtons. The person used an effort force of F to lift the wheelbarrow, and we're asked here to calculate the weight X of the load. Well, we should be familiar with the equation for weight. We should know that weight is equal to mass times by gravitational field strength. We should also be aware we're specifically in this question talking about the load, nothing else. So if we go through the question here, we can see that we're transporting a load of mass 20 kilograms. So in this case, we know that the mass is 20 kilograms. And we're also told in the question what the gravitational field strength is. We're told that it's 10 newtons per kilogram. So now that we have this, we can just put these into our equation for the weight. We can say that the weight is going to be equal to 20 times by 10. So that gives us 200 newtons for the weight. So we can just pop it into our line here, 200 newtons. So here we need to calculate the size and direction of the moment caused by the weight of the wheelbarrow. Let's remind ourselves of the picture. So if we're just looking at the weight of the wheelbarrow, we should be familiar with the fact that that is the 90 newtons. So let's just circle that in here. We can also see that the distance from the pivot, which is at the wheel, and this weight is 0.5 meters. So those are the numbers we need. We need to know that the equation for the moment of a force is equal to the force times by the distance between that force and the pivot, which, like I said, in this case is that wheel. So in the equation that you get given, it does state that that distance is normal to the direction of the force. And that is really important. It has to be at right angles to the force. And you can see that we do have that in this question. So now we have everything. We can say that the moment is equal to the force, 90, times by the distance, 0.5. And that gives us a moment equal to 45 Newton meters. Now looking at this question, you can see that we're also asked about the direction of the moment. Well, if we bear in mind that that pivot is at the wheel, you imagine that the force is pushing it down, it is going to rotate in this clockwise direction. If I ever feel a bit confused in a question about moments, whether it's going clockwise or anti-clockwise, I always like to just get my pen, hold the pen where the pivot is with my little pinchy fingers, and then push up or down with my other finger at the other end of the pencil, sort of replicating the diagram. So if I do that right now, if I get my pen in front of me, I hold onto it with my thumb and my forefinger on my left hand, and I push down on the right hand side, kind of replicating that wheelbarrow force. I can see it's going to rotate around like a clock in the clockwise direction. So that's what I do if I get a little bit stuck, okay? So use that tip yourself if you ever feel confused. But what we're going to add in here is clockwise. So now we're told that given that the wheelbarrow is in equilibrium, calculate that effort force required to lift the wheelbarrow. So to answer this, we need to know that if a body is in equilibrium, the sum of the clockwise moments is going to be equal to the sum of the anti-clockwise moments. And that's such an important statement. That's only true when the forces are balanced or in equilibrium, depending on how they're phrasing it. But that's going to enable us to calculate this effort force. If we have a look at the diagram and try and work out, okay, so where are these clockwise moments and where are these anti-clockwise moments, then that's going to help us. So we've already determined, haven't we, one of the clockwise moments. We said that the pivot is where the wheel is, and we said that the wheelbarrow, and we can actually see now that also that load as well are going to cause this wheelbarrow to rotate in the clockwise direction. So those cause clockwise moments. Whereas we must have some anti-clockwise moments. Well, looking at this, we can see that the lifting of the wheelbarrow causes a force that generates an anti-clockwise moment. So here we have some clockwise moments and we have some anti-clockwise moments. We can work those out and put them equal to each other. So let's get started with the clockwise moments, and let's start with X, that load. We know that the weight, we worked it out in part A, was equal to 200 newtons, and that has a distance of 0.3 meters to the pivot. So one of the clockwise moments is 0.3 times 200. There's another one though, isn't there, caused by that 90 newton force of the wheelbarrow's weight. We've already worked out that moment though, it's 45 newton meters. So now let's work out the sum of those anti-clockwise moments. Well, there's only one. It's going to be 1.2 times by F, or you could write it as F times 1.2. So now we've done that, let's tidy this up. We're going to have 60 plus 45 newton meters in the clockwise direction, which we can simplify to give us 105 newton meters clockwise. That's equal to 1.2 times by F. So we're nearly there now. All we need to do is rearrange this equation. F is going to be equal to 105 divided by 1.2, which gives me 87.5 newtons. So that is the size of the force F, that effort force required to lift the wheelbarrow and hold it in equilibrium. The person was offered a different wheelbarrow to lift the load. The new wheelbarrow had longer handles. The person was told it was going to take less effort to lift the load using this longer handled wheelbarrow. Describe and explain the effect this will have on the effort force required to maintain equilibrium. So this is a 2-mark question. So what we need to understand here is that that clockwise moment isn't affected in any way by this difference in the handles. The clockwise moment is going to remain exactly the same because the weight of the wheelbarrow and the weight of the load has stayed the same. So that's going to be our first point here. The clockwise moment remains the same, and as a result, because this is in equilibrium, we need to understand that if the clockwise moment has remained the same, then the anti-clockwise moment will also remain the same. So now we need to think about our conclusion here. We need to realise that to maintain this anti-clockwise moment, which hasn't changed, if we have the distance increasing, then the force must decrease. And this is because, of course, moment equals force times distance. Force and distance are actually inversely proportional. So as one gets bigger, the other one has to get smaller to counteract that effect. So the key things that we need to get into our answer here to get our 2 marks is, firstly, we need to understand that the clockwise moment remains the same. And the second thing we need to say to get our mark is that in order to keep the anti-clockwise moment the same as well, the force must decrease. In a nutshell, that's all we need to say. But what I've given you here is the full answer so that it can actually make sense, and I really hope it does. So just to summarise, remember the clockwise moment is unaffected, it remains the same. However, it's still in equilibrium, so the anti-clockwise moment must also be the same. And finally, as we know that the distance between the force and that pivot has increased, the force must decrease. And that is us having described and explained the effect this would have on the effort force required to maintain equilibrium. An investigation was carried out to determine the relationship between volume and pressure of a gas. A cylinder with a piston was placed in a water bath. A mass was placed on the piston and the volume of gas calculated. This was repeated with different masses to change the pressure. Suggest why we used a water bath in this experiment. So water baths are commonly used in science, and the reason why we use them in any of your sciences is to keep the temperature constant. So in this case, we're using it to keep the temperature of the gas constant, and that's all we've got to write. The results were plotted on a graph. Here you can see them. Here we're asked to describe the results shown in the graph, and this is a 3-mark question, so we want to be quite thorough with it. The first thing I always like to do in these questions is just state what the general trend is that I see before I sort of zoom in on it and look in a bit more detail. So I can see that as the pressure increases, the volume decreases. Now that's the initial thing I can say. I can see that it's a bit more complicated than that, but that's always a good starting point in these describe questions. For the second point, I would sort of zoom in a little bit more at a certain section, and I can see that if I look at lower pressures, any increase in pressure has a much bigger effect on the decrease in volume compared to at higher pressures. Obviously, you could say the opposite as well. You could say that at higher pressures, an increase in pressure has less of an effect on the temperature. Anything, so long as you're being much more specific with what's going on, and you're going to get the marks there. Now, the final mark we can say here is just to state what the relationship is between volume and pressure. And we should be familiar with the fact that volume is inversely proportional to pressure. And that really just links back to that initial point, as one of them gets bigger, the other one decreases. That's what inverse proportion is. However, because this is a 3-mark question, we want to state that here as well, okay? So here we've got our 3 marking points. First, just state the general trend. Second, be a bit more specific with a certain pattern that we see. And then finally, make that statement of the relationship between the two. So there we go, that's that question done. The results can be used to derive Boyle's law. Boyle's law states that pressure times volume is equal to a constant. Boyle's law also tells us that if the volume was changed, the pressure would also change. Explain why changing the volume of a container of gas would change the pressure of the gas. So because this question is just asking us about a change in the volume of a container of gas, we could either talk about increasing the volume or decreasing the volume and follow through the question using that method. Both are going to work. But here let's consider if the volume decreases. So if we decrease the volume and essentially close the walls in on this gas, we're going to see more frequent collisions of the gas particles with the walls of the container. Now every time there is a collision with the walls of the container, there's going to be a force exerted on those walls. Now if there's more frequent collisions, then of course in total we're going to see a much bigger force on the walls of this container. Now, a bigger force in total is going to have the effect of a bigger pressure. Now this is why if we, in this case, decrease the volume of a container, we will see an increase in the pressure of the gas. So these are our 3 key marking points when answering this question. The first thing we want to state is that as the volume decreases, we could give the converse. Here we're saying as the volume decreases, there are more frequent collisions of gas particles with the walls of the container, and each particle exerts a force on the wall of the container when it collides. Therefore, there's a greater force on the walls. So now we're told that when the gas in the cylinder has a volume 80 centimetre cubed, the pressure is 20 kilopascals. Here we're asked to calculate the pressure in the gas when it has a volume of 150 centimetres cubed. So we've got a couple of pairs of pressures and volumes involved here. Let's call 80 centimetre cubed V1 and 20 kilopascals P1. Here you can see we're asked to calculate the pressure in the gas when it has a volume of 150 centimetres cubed, so let's call 150 centimetres cubed V2. Now the reason why I'm doing this is because we should know that pressure times by volume equals a constant. We're given this equation, and what we can do to make that usable is we can state that P1 times V1, so A pressure times by A volume, is equal to another pressure times by another volume, so in this case P2 and V2. Now P2 in this case would be the pressure of the gas at volume of 150, which is what we're being asked to find. So rearranging this, I find that P2 is equal to P1 times V1 over V2. That gives me 20 times by 80 over 150. Putting that into the calculator, I find that the pressure of the gas is 10.7 kilopascals, and that there is our answer. So this method is how we harness that equation they give us, that pressure times volume equals constant. We can just take the pressure and volume of one set of data equals the pressure times volume of another set of data, and that's how it works. So it works out quite simple, really. I hope that that's making this topic of pressure and volume a little clearer. All charged particles and objects have electric fields around them. Here we're asked to describe what an electric field is. So another classic definition that if you don't know, then this is the perfect opportunity, there's no time like the present, for you to write down this definition. So an electric field is a region where charge experiences a force. And that's all there is to it. It's quite a simple definition, but it's one we definitely need to know. So the diagram below shows a negative particle. We're asked to draw arrows around the negative particle to show electric field surrounding it. So because this charge is a circle, we're going to have a radial field. Now all of the arrows are going to be pointing towards the negative, because electric fields travel from positive to negative. Now when drawing these field lines, let's make sure that they're evenly spaced, or at least by eye evenly spaced. And the reason for this is that around this spherical charge, if we're at an equal distance away from the charge, the force experience should be the same. So those equally spaced field lines represent that field being of the same strength. So there's the 2 key things that we need here. We want to make sure that the lines are evenly spaced and pointing inwards to this spherical charge. And I guess one final tip to give is don't just draw like 2 field lines or something. Make sure you draw at least 5 field lines in any question like this, otherwise they may not give you the marks. Here is an electric field diagram between 2 parallel lines. Explain how the diagram shows that the field is uniform. And this kind of calls back on the previous question and how I said about the importance of these evenly spaced lines. So here in this particular diagram, the reason why this field is completely uniform is because the lines are completely evenly spaced throughout. So now we're told that electric fields are responsible for the effects of static electricity. Static electricity has many useful applications, including using it to spray an even coat of paint onto cars. So here you can see that the car is connected to a negative electrode and the paint spray is connected to a positive electrode. Here we're asked to explain how this ensures that the car is evenly sprayed with paint. And this is a 5-mark question, okay? So we want to be very thorough in our answer. So the first thing that I would state is that all of the paint particles are going to have the same positive charge. Now we should know in physics that when we have the same charge, they're going to repel each other. Remember that opposites attract and like charges repel. So as a result, these paint particles are going to repel each other. Now, the direct impact on that is that the paint particles are now going to spread out. And this is going to have the direct impact of us having an even coat going forth onto the car. We're not going to get like big clumps in one area. No, it's going to spread out nice and evenly. So now, if we remember the diagram, the car is going to have the opposite charge to the paint. Now that's really important because, like we said, we understand that like charges repel and opposite charges will attract each other. So in this case, those positive paint particles is going to get attracted to the negative car. Now, the importance of this is that we're going to ensure that the whole of this car is going to get covered in paint. It's not just going to be one of the surfaces, no, it's going to be the back, the front, all of it. All of the little hidden areas is going to get covered in paint because of that attraction between the positive paint particles and the negative car. So here we've got 6 different significant points. The question was only a 5 marker, so we only needed to state those down to get our 5 marks. However, none of them were particularly complicated. I think you could see that those points all tell quite a story. And in the long mark questions, always imagine that you're almost telling a story. You want to start right at the beginning and then you want to get to the end. So let's have a look at the next part. As well as having many useful applications, in certain situations static electricity can be dangerous. Here we're told to state one dangerous situation that can arise from static electricity. So this could almost be considered a bit of general knowledge. I think you could probably get 1 mark with your general knowledge, or of course we've learnt a few. So one example is lightning. One example is that it could cause an explosion. And also another thing is that it could potentially ignite flammable materials. Now, if you've got another great example that shows the dangers from static electricity, then by all means write that down. The mark scheme will allow for anything that is correct, but these are the 3 that you'll be familiar with from learning in class. So in the exam, if you write down any one of those, you're going to get your mark. A dynamo is a direct current generator. Some bicycles use dynamos to generate electricity to power their lamps while the bicycle's wheels are turning. So here we've got a nice little diagram here. You can see we've got this split ring commutator and brushes as well. And we're asked to describe how the dynamo induces a current in the wire. Now this is a 3 mark question, so we need 3 good points to explain this. This is one of those quite tricky questions. So if you're not 100% of this already, then use this as an opportunity to get these down on your flashcards right now. Okay, so the first thing that we're going to state is that the coil is going to move through the magnetic field, or we could state that it cuts through magnetic field lines. That's our first point here. Okay, so on to our second point. So we should be able to state that therefore a potential difference is induced as our second key point that we need to say. And then finally, because the question's asking about how it induces a current in the wire, we're going to state that because we have a complete circuit here, a current is induced. And those are our 3 key points that we need to state to get our 3 marks here. So if you're not familiar with this, then get out a flashcard, pause this video now, and write it down. Now we're asked to explain the importance of the split ring commutator. And this is a vital part of a dynamo. So this is a 2 mark question. We need 2 key points. I'm going to write down 3 points here, but pick whichever 2 you're the most comfortable with. So the split ring commutator is able to change the coil connections every half turn. Now, this means that as the induced potential difference is about to change direction, the connections get reversed. Now, the consequence of this is that when we induce this current, it always flows in the same direction, which means that this dynamo is inducing a direct current. So these are 3 key points that we can say to be able to, of course, get our 2 marks. you only need to state 2 of them, the most suitable 2 that for you makes sense. However, it's always good to learn all of them because, let's be honest, today it's a 2-mark question, tomorrow it could be a 3-mark question. And if you only learn the bare minimum in a question, then you're not setting yourself up for that worst case scenario, that most challenging question. So there we are. There are our 3 points we could write down to explain the importance of the split ring commutator. So for part C, we're asked to complete the graph to show how the induced potential difference varies with time as the coil moves through one complete rotation of the coil in the dynamo. We're assuming that at t equals 0, the coil is moving parallel to the direction of the magnetic field. Now, when it's parallel to the magnetic field, there's no field lines getting cut. So as a result, if we think of what we said in A, if there's no field lines being cut, then there's no potential difference being induced. So at 0 time, there's 0 potential difference. It's then going to go up to a maximum and then down back to 0. And it's not ever going to go negative because with a dynamo, it's making a direct current, it's just going to bump up again. So if we just think about what each of these mean. Initially, the coil is moving parallel to the direction of the magnetic field. Now that means if these pink lines are the field, that there's no field lines being cut, and therefore there's no induced potential difference. However, when it's rotated to 90 degrees, what we have now is we've got the maximum amount of field lines being cut, because that motion is perpendicular to the field lines. So that's why at what would essentially be when it's at the orientation 90 degrees, we have a maximum. Then it bumps back down to 0 because then when it gets to a 180 degree rotation, we're back at square one essentially, just upside down. We can see that the coil is moving parallel to the direction of the magnetic field. So then again, we'll be at essentially 270 degree rotation now. We can see again, we're essentially sort of back to that orientation where it is moving at right angles to the field. So we've got a maximum induced potential difference. And then finally, we finish up back 360 degrees at that start point. And so we finish on 0 because we're back to being parallel to the direction of the magnetic field. Now, we can of course just learn the graph as it is. However, I think it makes it make more sense if we can think about what's happening. Now, all that I was trying to explain with these little diagrams is that we need that motion to be perpendicular to the field lines to get the maximum induced potential difference. And if they're parallel, then no field lines are getting cut at all, and we get 0 potential difference. So now we're asked to state one change that can be made to increase the size of the induced potential difference. There's 2 things we could say here. We just need to state one, but it's worth learning them both. So the first thing we could say is we could just use stronger magnets or a stronger magnetic field. That is certainly going to increase the size of that induced potential difference. Secondly, we could increase the frequency of rotation. What both of these things are doing are increasing the number of field lines being cut any second. Through stronger magnets, that's because there's more field lines, they're going to be closer together. Whereas when we increase the frequency of rotation, what we're doing there is we're moving that coil more quickly, which means that in any second, it's going to cut more of those field lines because it's going to rotate through them more times. So both of those are good ways we can increase the size of the induced potential difference. So for the last part of this question, we're told that dynamos generate direct current and alternators generate alternating current. We're asked to suggest what changes could be made to a dynamo to convert it into an alternator. So there's one simple change that we can make here, and that is replacing the split ring commutator with slip rings. Now that is going to be all you need to do to now have an alternator rather than a dynamo. And the reason for this change is, of course, remember we wanted the split ring commutator to be able to reverse the connections every half turn. We don't need that now when we have an alternator where we're making this alternating current. So as simple as that, perfect for a flashcard. How do you change a dynamo to an alternator? Replace the split ring commutator with slip rings.
Well done for making it to the end of this video. I'm really, really proud of all of your hard work.